Well, good afternoon, ladies and gentlemen. I want to welcome you all to the Woodrow Wilson Center. My name is Jeff DeBelko. I'm very fortunate to direct our Environmental Change and Security Program. Welcome you to Washington in the summer on another hot day where I'm trying to set an example and issue jackets for the rest of the summer. So I'm encouraging you all to come informal for some really dynamic discussion here at the center. We're very pleased to be discussing healthy solutions to climate change with really two leading scholars who also are very much part of a practitioner in a policy world, which in many ways is exactly what the Wilson Center is trying to do, reflect this legacy of Wilson as our only president who had a PhD and was distinguished in the academic world and then distinguished obviously in the policy world, bringing these worlds together. So Paul Epstein and Amanda Staudt are certainly two who fit that bill in a series of discussions that we've tried to have here at the Wilson Center around issues of environment, in this case climate change, and health. And so it's exactly what we're tackling today, a day that, when we didn't plan this, I must say, but a day that the U.S. government released a NOAA-led study, Global Climate Change Impacts in the United States, one that is really going to give us a picture of what the expected impacts in very specific regional contexts are going to be, something that I think is going to be very useful and may, in fact, have some of our speakers having to run off for TV interviews and such. It's a big day for climate change, to be sure. Just a word about the Environmental Change and Security Program. I mentioned the Wilson Center is trying to facilitate this dialogue between the worlds of research and policy on a non-advocacy, a nonpartisan basis. Our Environmental Change and Security Program does exactly that with issues of environment, health, population development, and at times even foreign policy and security policy. So we're very pleased to have this discussion today and have the continued support from USAID's Office of Population and Reproductive Health and the Bureau of Global Health at AID to make these discussions possible. In the order that they're going to speak, Amanda Staudt is a climate scientist with the National Wildlife Federation, where she's providing a range of advice on issues, a big focus on the Chesapeake. Also, before that, was a senior program officer at the National Academies, involved in a lot of their studies and reports, and so really has this kind of broad scientific perspective, but also very much grounded in the practitioner world as well. And then Dr. Paul Epstein is Associate Director of the Center for Health and Global Environment at Harvard Medical School. We've had very good fortune here in the last couple of years to have now Paul and before his colleague Eric Chivian come and share their expertise. It's really a very dynamic program that Paul is part of, and as you will see in the bios that we circulated, he's really been on the forefront of the research and on the forefront of trying to make sense of this in a very practical and applied policy realm. The IPCC, the Millennium Ecosystem Assessment, really making some fundamental contributions in this area. So I'm going to turn the floor over first to Amanda, and then we'll hear from Paul, and then we'll have a Q&A at the end. Please.
Thank you so much for inviting me here. It's very exciting to be here. And it's really an honor to share the stage with Dr. Epstein. I was telling him before we started that when I was an undergraduate, he came and gave a guest lecture in one of my classes at Harvard. And that was my first introduction to the impacts of climate change on health. And Dr. Epstein was quite at the forefront of thinking on that in the time, and and still is at the forefront of thinking on these issues. So it's really a pleasure to be able to share the stage with him today. Let me just get this started. I always say that people lose all sense of how to do anything when they get in front of an audience. So F5, that's the easiest way, huh? Okay. As Jeff mentioned, today's a very exciting day. The U.S. government released a long-awaited and very impressive and comprehensive report on climate change. Unfortunately, I had to provide my slides to you guys before the report came out, and it was embargoed, so I couldn't include any of the results from that report in my remarks. But I may try and mention some of the findings from that as I go along. They had a press conference at 1:30 today. with John Holdren, the President's Science Advisor, and Jane Lubchenco, the head of NOAA, among other scientists who helped author the report there. And I think this is just a little remark on that report. It's just a very exciting opportunity in that it kind of finally puts together a comprehensive look of how climate change is already impacting the United States. It's very clear about that. And then it puts forward two choices in terms of our future, a lower emissions pathway and a higher emissions pathway. And is very clear about the fact that taking action soon to reduce our emissions can help reduce the impacts of the severity and the impacts and the cost as we go forward. So I urge you to check out that report at your earliest convenience. I'm sure it'll be all over the news. So my job this afternoon is to help set the stage, provide some of the broader context. And what I'm going to do is focus on a sampling of some of the recent science, and in particular focusing on some of the scientific findings that I think underscore the urgency of the issue right now. And I'm also, because I work for the National Wildlife Federation, there'll be a little bit of a flavor of wildlife and conservation. I'll give you a little bit of input from that community as well. So let's get started. To start off, I would say there's absolutely mounting scientific evidence. Actually, when I first put this together, I put overwhelming scientific evidence, and I thought, well, maybe that's overstating it. But I mean, certainly the evidence is growing and growing. And if I were to sort of characterize the flavor of a lot of the studies that have been coming out since the IPCC in 2007, I would say that we've seen increasing sense of urgency in their findings. That there's a sense that climate change is happening faster than what we had anticipated even a few years ago. And I'll present some studies that illustrate that point. Second, I would say that there's an increasing awareness that many of the changes are going to be irreversible. I don't know about you, but even as someone who's been thinking about climate change for a long time, I always sort of had this sense that, okay, we're just going to get our hands around this problem, we're going to solve it, we're going to kind of go back to normal. And that really isn't the case, and there have been several studies that have kind of very clearly made that case recently. Third, I think it's an increasing awareness that we're already being impacted. In particular, the increasing severity of weather and climate extremes, droughts and floods and rainfall and hurricanes and wildfires are all ways that I think we're experiencing global warming in our day-to-day lives already. And I'm actually not going to talk about this because Paul has a lot of it in his talk, so I figured we wouldn't overlap there. But I think that is another feature of a lot of the scientific studies that are coming out. And then finally, all of this sort of brings an increasing attention and emphasis on solutions. And so I'm going to end my talk giving you a little bit of a flavor of some of the discussion around particularly the ACES Act, that's the Waxman-Markey Act that's being discussed in the House right now. Okay, so let's talk about the urgency. And I like to put on my picture of a pot just about to boil over, because I kind of feel like that's where we are. We know there's a problem. So I have 2 little boys, and whenever I'm cooking pasta, I always get to this point because I'm watching them and not paying attention to my stove. And it's like, if I can just get there in time, I will not make a complete mess of my stove. And I kind of think we're at that point now. We need to get there just in time so we don't make a complete mess and get that pot off the stove and start taking some action. And what are some of these studies that are starting to underscore the urgency? Well, one fact is that the emissions appear to be increasing faster than the worst case scenario. So this plot shows in the colored lines the projected emissions, and the black line shows the actual emissions of carbon dioxide over the last decade or so. And you can see that over the last 4 or 5 years that we've had an uptick in our rate of emissions. In fact, the emissions are increasing at a rate of 3.3% a year right now. And the authors of this study found that there were several reasons for this increase in emissions. One is that the developed world isn't reducing their emissions as quickly as anticipated. They aren't increasing their efficiency and moving to renewables as quickly as anticipated. Second, there are more and more emissions from the developing world, and they're increasing faster than expected. And third, the one that I think is a little bit scary because we can't do much about it, is that some of our natural sinks are less efficient than what we had thought. So as you may know, a large fraction of the carbon dioxide that we emit into the atmosphere is absorbed in the ocean in the terrestrial biosphere. And there have been recent studies that have shown that the uptake of carbon dioxide into the ocean is not as great as what had been anticipated. So the blue line shows the expected uptake, and the red line shows the actual observed uptake. And you can see that there's a significant disparity there between those two levels. And what this indicates is that, if we have less carbon uptake, as we continue to put carbon into the atmosphere, we have the potential for more warming. And of course, putting carbon in the ocean also leads to ocean acidification, which is another issue I'm not going to talk about, but just point that out, that this is all kind of related. Okay, another piece of evidence that the global warming may be happening faster than we expected is the Arctic sea ice story. And the blue line shows what the scientists had thought that Arctic sea ice decline would look like over the next 40 years. And the red line is the actual observations of what happened. And you can see, especially if you look at 2007 and 2008, which I've added in after this plot was produced, that there is significantly less ice than what the models had anticipated. And in fact, there are two recent studies that have looked at this, the recent years, so 2007 and 8, and one found that the minimum in 2007 would not have been possible without the sustained warming that we've had over the past few decades and the long-term ice reductions. So there had been some discussion that maybe we're just seeing some natural variability, but a recent study came out and said, no, this really is global warming. And a second study recently came out and said that the total volume of ice in 2008 was likely a record low. So even though the area was a little bit higher than 2007, if you take into account the whole volume, it's actually lower. Well, this is particularly problematic for polar bears and also walrus and sea lions, which don't seem to get as much press, because they depend on sea ice to hunt for their prey. But it's also concerning for us because as we lose our sea ice, we have a reduction in albedo, which is the reflectivity of our planet. And that means that, that when the sun's energy hits our planet, more of it stays here instead of being reflected back to space. So this is another way in which we could be increasing the speed of global warming. Okay, a third example where the impacts seem to be perhaps worse than anticipated, and this is in terms of forest mortality. This study came out just recently, and they found that they looked at forests that are old-growth forests that haven't been affected by development or humans too much, and they found there's widespread mortality in these forests. All the red dots and the size of them indicate places where the mortality has increased because of increased heat stress and because of increased drought stress. So unfortunately, the young trees are not keeping up, so we're actually seeing a thinning of our forests in these places. If you add on to the fact that we're seeing a factor of 4 increase in the number of wildfires in the western U.S., and the area burnt by those fires is a factor of 6 greater since the mid-1980s, it really starts to add up that our forests are under attack. And probably the most dramatic image of our forests under attack is the widespread pine beetle infestations. All these rust-colored trees have been infected by pine bark beetles. And the infestation right now is affecting millions of acres in the western United States. So our forests are really under attack. And the thing that's a little bit concerning about this for me is that when you lose your forest, you're actually releasing the carbon that was stored in those trees back into the atmosphere. So here's yet another way that we could be accelerating the warming. And it's something to consider as well as we think about policy and looking to our forests as a place to continue to sequester carbon. We need to do that in a way that's mindful of the fact that our forests are being affected by global warming at the same time. All right, so those are a few examples. Oh, one more, sorry. Melting permafrost. In the frozen tundra in the Arctic and on the bottom of the Arctic Sea, there is a lot of methane stored. And melting of that permafrost can actually release that methane to the atmosphere. The picture on the left is of Dr. Katie Walter. She's a professor in the University of Alaska in Fairbanks. And what she does is looks for lakes where there's been melting that have been created by melting permafrost. And as that permafrost had melted, the lake is created and methane is released. In the wintertime, the lakes freeze over, and so the methane is bubbling up from the bottom of the surface of the lake and collects between the top of the water and the bottom of the ice. And so what Katie has done here is poked a hole in top of that ice and released the methane and set it on fire. And actually, there's a video of this where she pokes again and it flames up. And it's a really dramatic vision of how our planet is starting to release some of its stored greenhouse gases into the atmosphere. The map on the right shows places in the Arctic where these thermokarst lakes, these lakes where there could be methane are, and the status of the permafrost is indicated in the color. So you can see there's a wide area of places where this methane release could take place. In fact, it's estimated that the lake bottoms have as much as 10 times more methane than is currently found in the atmosphere. And if you don't know, methane is a greenhouse gas that's about 20 to 25 times more potent than carbon dioxide. So a little bit of methane can go a long way. There's also methane at the bottom of the Arctic Sea or Arctic Ocean, and there's been a study to examine whether that methane might be destabilized and released to the atmosphere. And they focus on this area off the coast of Siberia. So the next map is going to be looking at just that box. Okay, so now you're looking down on the box, and there's the coast of Siberia in gray. And what they've done is gone back twice over a period of 10 years and measured the methane at the bottom of the ocean, in the ocean surface, and in the atmosphere. And what they found are these plumes of methane being released from the bottom of the ocean into the atmosphere. And the speed of this release is about 10 times faster today than it was a decade ago. So the chances of a massive methane release are actually pretty low, but the fact is there's a lot of methane stored there, and so the risk involved is very high. So that's why we're particularly concerned about this potential change in our climate. All right, now I want to talk a little bit about some irreversible changes. And I put this picture up here because I think aridification or drying out is going to be one of the most serious ones that will be affecting people and ecosystems. There's several studies that have come out in the last couple years that have looked at the shifts to more semi-arid conditions. And this is one done by Susan Solomon et al. That came out in the proceeding of the National Academy of Sciences. And what they did is they looked at how our climate will change over hundreds and thousands of years. And they looked at different stabilization levels of carbon dioxide in the atmosphere. And what they identified were several regions around the world, that these bright red and pink colors, where there is a pronounced drying out in the dry season. And the southwestern United States is one of those, and there's already been some papers coming out that say that area is beginning to dry significantly. And so let me show you this map that goes along with this, or this chart, I'm sorry. This says, if you look across the top, it shows you the quasi-equilibrium carbon dioxide concentrations, so stabilized carbon stabilization levels. And then the lines indicate the level of drying that would be associated with that stabilization. So actually, maybe I'll walk over here. So if you stabilize at 450, this is the southwestern United States, you would see a drying of something like 15%. And this area indicates the range of observed past droughts. So basically, stabilizing at 450, which is where we're going right now, would create semi-permanent situation like the Dust Bowl. Does that make sense? It's a little complicated, but basically what the study comes out to say is that the Southwest United States and several other places around the world are on track to be converted to semi-arid conditions permanently. Sea level rise is another change which is effectively irreversible in our lifetimes. And on top of that, I think the projections are starting to be higher for what kind of sea level rise we'll see this century. The IPCC in 2007, the range that they gave in their report was between 7 inches and 23 inches. And so that's this range here. And some recent studies since then have actually taken into account the rapid melting that's been observed in Greenland and Antarctica in recent years. So if you project forward or extrapolate the recent melting, you actually get a range that's much higher, something like 2.5 to 6.5 feet. The minimum you would get if you extrapolate the recent trends is greater than the maximum that IPCC put forward. Now you might say this recent trend is not going to keep going that way, that perhaps it doesn't make sense to extrapolate it. So there's another study that looked at this another way, and they went back and looked historically over the last 2,000 years using paleo records at temperature and sea level. And they did a correlation, and then they plugged into that correlation the temperatures projected for 2100. And what they find is a range of sea level rise in 2100 of between 2.5 and 5.5 feet. And so what I take away from this is that 0.5 foot to 2 feet range is very, very conservative. And in fact, the report that came out today from the CCSP, they focus on a 2 to 3 feet sea level rise by the end of the century and acknowledge that it could be as much as 4 to 6 feet. So this is, if this happens, it's effectively an irreversible change. And I want to show you some of the modeling we did for the Chesapeake Bay region and show you how that region would be dramatically impacted. This is the Blackwater National Wildlife Refuge, which is on the eastern shore. It's a very famous place for waterfowl, Canada goose and those, and as well as for a number of fish use it as a breeding ground. If sea level rise were to increase just over 2 feet, let me say the purple outlines are where the National Wildlife Refuge is right now. Sea level rise of just about 2 feet. Actually, this is what it looks like. Most of the marsh and other land that's in part of the wildlife refuge is underwater. It's open water. So I can go back and forth for you. You can see it's a pretty dramatic loss of land in that case. Species extinction. Here's my wildlife flavor. This is another basically irreversible change to our planet. So here's a sort of map of 2 different temperature pathways. One if we stabilize at 450 ppm, and another if we go on a business as usual pathway. And let's look at the impacts on global species and habitat in North America. Already at the temperatures the warming we've had so far, we're already seeing increased extinctions of mountain amphibians. If we continue, as we are likely to do, to stabilize around 450, we're going to see species committed to extinction of around 9 to 31%. And the habitat in North America for cold water fish, about 8% of it will be lost. I see Susan walking up here, which means that I got a call from folks about perhaps doing some news stuff today, but it's okay. I'll call them back in a few minutes. Yeah. Thanks, Susan. And then if temperatures continue to increase, if we don't do anything to reduce our emissions, we're looking at up to 50% of species globally committed to extinction. And I personally think that's just unacceptable. How can we allow half of our species on the planet to be committed to extinction? And also a major decline in the prairie pothole habitat. That's the main breeding ground for waterfowl in the United States and in Canada as well. Okay, so let's talk a little bit about solutions. And I'm not going to go into a lot of detail about this because it's not really what I focus on. But I think it's important to recognize that there's a lot going on right now in terms of solutions. And what I've presented so far I think is a little depressing, but I think there are a lot of good opportunities for moving forward, both on the mitigation side and moving to renewables and reducing our emissions, and on the adaptation side. And what I show on the right here is one of the options for helping wildlife adapt to climate change is creating corridors where wildlife can migrate to new habitats if their current habitat becomes unsuitable. So I just wanted to talk a little bit about the American Clean Energy and Security Act. That's the bill that's currently being discussed in the House right now. This is what the bill puts forward in terms of its emission pathway. The red line shows business as usual. The green line shows the reductions expected with the emissions caps under the cap and trade system, which gets down to about 15% below 2005 by 2020 and 73% below 2005 by 2050. Then the bill has some other complementary measures in encouraging the use of efficiency and renewables and such, which it's thought could improve the emissions reductions, especially in the short term, and get the near term, the 2020 emissions to as much as 33% below 2005 levels. And so this is largely achieved with a cap and trade system that puts a cap on emissions, and then sells allowances for big emitters to emit carbon dioxide. And one of the features of the bill is that it then allocates the income from those allowances to various public goods. And I thought you might be interested in seeing how the bill does its allocations right now. And this is the version that came out of the Senate or the House Energy and Commerce Committee at the end of May. You can see a big part of the allowances goes to the fossil fuel transition. That's mostly helping the electricity sector and make the transition. There's a big amount that goes to encouraging R&D of green technologies. Some money that goes to help low-income consumers who might not be able to afford the increase in their electricity bills under the cap and trade system. And then little bits that go to some other public goods, including natural resources, which is in red. And I highlight that just because that's the one that we've been thinking about a lot at the National Wildlife Federation. And I'll talk a little bit about how they do the natural resources. It's actually allocated to a range of different agencies, states, and tribes. And it averages out to be about $1.7 billion a year that's divvied up in this pie through 2030. And you can see a whole bunch goes to the states. And then, as I mentioned, these different agencies. And so how would this, and this money is dedicated for helping natural resources adapt to climate change, those changes that we can't avoid. And it really is an opportunity to transform conservation. I'll just say that the conservation community right now is actively wrestling with how global warming will affect their mission. For many years, perhaps the whole history of conservation, the emphasis has been on returning our wild lands to some previously pristine state. And that just is not a reality anymore. We're dealing with completely new climate conditions. And so now we have to think in the conservation community about how we change everything we do to make sense in a changing climate. So this dedicated funding would be the first to really focus on helping species, habitats, ecosystems, et cetera, survive climate change, and it also includes a piece for ocean acidification. And it requires the development of adaptation plans at the state level, federal agencies, and a national one that brings that all together. And right now, many of the states and federal agencies are actively in the process of putting together these adaptation plans in anticipation of the fact that they're going to be required to do it at some point. So that's a little flavor about where things are right now. I just want to end with some personal reflection. This is actually me with my kids and a coworker at a rally last year in support of the Senate Warner-Lieberman bill. And for me, I just think this is a really historic opportunity. Everything's kind of coming together. We have increasing certainty and awareness about the urgency from the science. So we know we need to reduce global warming pollution. At the same time, we have this opportunity to repower America, advance a clean energy economy, and also protect wildlife for our children's future. And that's really why I'm in this game at all. I think it's just so important that we be taking action now as soon as possible to start providing a better world for our children going forward. So I will end there. Thank you. Paul's going to come up then.
Terrific. Dr. Epstein?
Oh, boy, that was quite something. I want to thank Jeff and Gib and Rachel and also Noel Gerwick for organizing these connections, and just mention my friend Steve Dissart from Swiss Re, with whom we've worked for years on the health and economic dimensions of climate change. And to Amanda, that was amazing. That was a wonderful talk, and maybe I think we all need a moment just to digest it. So, get some water. It's nothing to be sorry about.
We're happy to be a warm-up act for your sound bites. I don't think they'll give you quite as much time.
Yeah,
but yeah. That's right.
Thank you.
Thank you, Amanda.
Great. Well, this is some of the biology behind and below, and some of what you've just heard. And my friend often calls the subtitle of my talk, "It's Worse Than You Think." I think we have a competitor for that just a moment ago. That was quite a panorama of where we are and how much further along we are than we thought. I'm going to talk about climate change in just a moment, then impacts, and work to what's in our backyard, and hope to arm all of you with as you work on these issues here, and then finally turn to solutions and think about how we can divide what we can do right away and what we need to study so that we don't wind up with a whole new range of unintended consequences and stranded assets. Interrupt me at any moment. I'm going to take your advice. It is warm. And then we'll have time for discussion after. Okay, this first two on climate just recaps some of what you heard, but puts a little bit in context. Here we are with the ice cores back to 400,000 years, going between large caps and medium-sized caps. This goes back to 800,000 years in the ice record. It probably goes back 2 million years, because that's when the Panama Isthmus closed off and the Gulf Stream got started. And that's the part of the conveyor belt which helps stabilize climate for millennium. So here we are, stable states. The Earth likes stable states, like we all like stable states. And we're awake and then fall asleep. That's another stable state. It's actually our reticular activating system kicks off. That's what sometimes jerks you when you fall asleep. So there are stable states, and the Earth likes these, going from medium-sized to large-sized caps. Here we are with rates of change, variance around the mean increasing, a sign of instability. And for the biology, variance is not just the noise, it's become a signal. As we look at mosquitoes and so on, variability is a big part of the impacts of climate change. Major outliers, punctuated equilibria. This is the theory from evolutionary theory, that we're stable for long times and then go through transitions. Earth seems to do that as well, go through transitions rather quickly. So here we are, 280, 180, medium caps. We're up at 387. We're outside this envelope that we've been in probably for 2 million years. So this is the real hard ice data on where we are relative to where we've been for probably 2 million years. Those cycles being driven by the Earth around the sun, the orbits, the eccentricity, the wobbles, the Milankovitch cycles. That's your natural variability. So what we're seeing is natural variability and climate change affecting our weather. Second issue, which you heard a little bit about, methane. Just to add these up, the IPCC did add these up, and the forcing factors are much greater than 387, 460. That's not the whole story. We get the SOx's, the sulfur oxides of sulfur, and their cloud condensation nuclei, and that cools things. Low clouds cool, high clouds tend to warm. So sulfates, we thought we'd clean the sulfur out of fuels, things would warm up more than we thought. Well, here's the silver lining in this black cloud. It's the black soot, the particulates, black carbon. And we now know that it's a very big forcing factor. Here's 1.6 watts per meter squared. Think of a little Christmas light, LED. Think LED light on the ground. And this is about 2/3. Carbon dioxide lasts 100 years. Black soot lasts 8 days, depending on the rain. So the good news is, if we clean up fuels, we may not warm up as we thought, but we actually will reduce a warming factor. Here's the brown haze over Asia, which we've known is contributing to climate locally, but now we know it's a global issue. Some of this is we don't know exactly where we are, and the third issue is ice melt that you heard about, and how many saw Inconvenient Truth? Great. I urge all to see it. The only problem is he tends to underestimate. That's a joke. My good friend Al. Ice melt. As we lose ice shelves, it doesn't raise sea level, but it does take back pressure off the ice sheets. And this is what's happening in Greenland. It's happening in Antarctica. Just as on Cape Cod, if you took the sand down, the dunes come down. Those ice shelves buffer and buttress the ice sheets. So we're seeing an acceleration of ice sheets. The biggest one we know it's coming down here is the Luciat, the Jakobshaven, and you'll remember it because it shed the icebergs that sunk the Titanic. That's the one right off of West Greenland. It's coming down now twice as fast as it did in the 1990s. Twice as fast is non-trivial. We're talking 7 kilometers and now 14 kilometers a year. They're not all going that fast, but that's the fastest. So the behavior of ice sheets is one of the main issues. And as Amanda mentioned, the calculations are changing. 5 years ago, sea level rise was half from thermal expansion, half from ice melt. Today, it's 80% ice melt. It's dramatic, and it's very much different than when the IPCC finished up in 2007. Sea level rise mentioned. Albedo, the Earth's albedo overall is about 30%. 30% is going back up into space. If it goes down to 29, 28, that could be a trigger point. We don't know where that might be, but that's another issue with more heat going into the open ocean, more melting of ice, more heat in the ocean. You get the idea. A positive amplifying feedback that could warm. Here's the sea ice. You saw this before. It's just dramatic. This is what really alarmed even the non-alarmists, what happened in 2007, and then it, in winter, went back up, and then not quite as much, but as Amanda said, the volume. Okay, the other part of this story that we hear little about is what's happening in the oceans. This is the work of Sid Lebedes and his colleagues at NOAA, our Department of Commerce, taking all of the data from buoys, from satellites, from submarines since the 1950s. 1957 was the first IGY, the first International Geophysical Year. So a lot of global research began then. The oceans have warmed 22 times as much as has the atmosphere. 22 times. That's a number to remember. It's the amount of joules, exajoules, that's 10 to the 18th joules. It's not temperature, it's heat content. As we know, water warms up slower, and it also releases its heat slower. And that's what's happened over the last century and a half, is it's warmed up slower. That's the capacitor for last century's global warming. It's what connects global warming to climate change. Climate change is warming and a change in the weather patterns. And it's through the oceans and the change in the hydrological cycle that global warming is affecting the climate and causing climate change. Looking for a blackboard here, but it's weather patterns are changing. Winds are changing. That's one of the things not stressed enough about the IPCC recently. The westerly winds in both hemispheres, more in the southern. Think drought in Australia and winds there that are affecting the continent's hydrological regime. But it's weather that is changing. And what we're seeing in a way, as warming occurs, we'd think that this bell-shaped curve of the distribution will just move over to the left. Everything will get a little warmer, and we'll see more weather in the high tails. We're seeing in the low tails, the high tails. We're really beginning to see a bimodal distribution where there are fewer normal, shall I say, average days, and more cold, more hot, more dry, more wet, more punctuations and sequences of extreme. So this is the physics behind it. Water is warming, ice is melting, water vapor is rising. Those are the three states that water exists, plus snow. That's the other ones. Our sense of snow, that's a fourth. But the main ones are speeding up, and we're seeing more water vapor in the atmosphere. And for every 1 degree centigrade the atmosphere warms up, it holds more water vapor, 7%. So we've got a push and a pull on the water cycle, and this is what's drying out parts of the land. And when rain comes down, it comes down in heavier downpours. So here's the numbers over the U.S. from your NCDC, National Climatic Data Center in Asheville, North Carolina, part of NOAA. Rain over the continental U.S. up a little bit. 2 inches a day, up 14%. That's an important number because that's the number that we associate with waterborne disease outbreaks like E. coli, cryptosporidium. That's what drives sanitation into clean water supplies. So that's critical, and we've mapped that across the U.S. 4 inches, they've gone 20%, and then just released is that 6 inches a day, half a foot of rain a day events have gone up 27%. Again, the shift to the outliers. Here's the biggest one we know. In the last 1877 is our records. 1 meter of rain in a day in Mumbai with all of the consequences, not only just acute, but the conditions for outbreaks of mosquitoes, waterborne, and so on. Okay, that's the climate story. What does that do to our health? The clearest signal we have in terms of infectious disease is in the mountains of Africa, Asia, Latin America. What we're seeing in Kilimanjaro and in the Tibetan Plateau and the Andes is that glaciers are retreating, plant communities are upwardly migrating, and mosquitoes that cause malaria, dengue fever, and so on are circulating at high altitudes. There are 3 sets of maps behind this that I can make available for you to put on the web that give you the data, sort of a simple person's GIS of mapping where the glaciers, where the mosquitoes, where the plants are moving, and they are very confluent. In fact, the temperature of the freezing isotherm, the level at which it's frozen all year round, is bumping up. That's our weather balloon. So there's 4 sets of data. That's the key way we know that climate, in terms of warming, is affecting infectious disease. Mountains are great to study, primarily because of their wonderful verticality. You go from deserts to rainforests to the poles to climate in a matter of miles. If you go up 1 mile, it's equivalent to going 600 in latitude. So this is a very clear sentinel area. It's also material because malaria is circulating in Nairobi, a mile-high city. Dengue fever in the mountains of Vietnam. Dengue fever, yellow fever in the Andes. So this is having an effect already in the central highlands of Africa and so on. Turning to lovely Africa. Here's just to orient you with the map. Here's the four rivers, the Congo, the Niger, the Nile, and this is the Zambezi. Here's the Great Rift Valley where we're all from, and the lakes and so on. But here's the Sahel, the meningitis belt, we call it. It's one of the infectious diseases that's not vector-borne. It's person-to-person. We think that drought accelerates this because it dries out the membranes. There's a helpful story behind this, which is that we can vaccinate against meningitis. And so if we have early warning systems, the health early warning systems that NOAA is trying to develop now, we've been working on this for 15 years, but now with this administration, we're going to really have some climate services so that people in Niger, et cetera, can vaccinate when they know there's going to be a drought. So this can be helpful with early warnings. Here's a problem we just learned we didn't know we'd had: chikungunya fever. It's like dengue fever, which is called breakbone fever. I warned you this is worse than you think, so bear with me. And things come and go. There are cycles to these things. But here's this one that broke out in East Africa after drought. We've known that Aedes aegypti, which carries this, that carries dengue fever in Puerto Rico, in Cuba, and so on, in the islands of the Caribbean. When there's drought, people store water around their houses, breeds this very short-flying mosquito, Aedes aegypti. So that's what happened in East Africa. There were 500,000 cases. It then spread throughout the Indian Ocean, which is overheated. There was an outbreak in Italy in 2007. That was on the front page of the Times. This is global warming. It's the extension of the range. Maybe yes, maybe no. It's hard to say. This was an Asian tiger mosquito, Aedes albopictus, which we have in the United States. It's a vector for West Nile and so on, but not a good one, fortunately. But it was good enough in Italy. So maybe yes, maybe no, but the real issue with this disease is the drought that intensified the conditions conducive to. And those are three key words in thinking about infectious disease. Then that drought yielded to heavy rains, and we got other problems: mosquito-borne, rodent-borne, waterborne. RVF is Rift Valley fever. That's a disease that gets cattle and ungulates. It also affects humans. It affects livestock. So it affects the manure in the field, and agriculture affects trade. It's a big issue economically. It's an issue now that's transferred to Saudi Arabia. Amanda talked about the bark beetles, so let me just give you a couple of bits in the background here. Here's the agent. Here's the host, here's the environment. That's the epidemiological framework. TB doesn't cause TB. You need a host that's immunodeficient and an environment that's conducive. In this case, absence of killing frosts mean that beetles are overwintering, moving to higher altitudes, moving to higher latitudes, even getting in more generations each year. What's happening with the trees, the host in this case, is repeated extremes, particularly drought, dries the rosin that drowns the beetles as they try to drive through the bark. So the extremes weaken the host, warming's emboldening the pest, and the environment certainly conducive. And here's the Kenai Peninsula in Alaska, 4 million acres just there alone. And this brings Weyerhaeuser into the discussion to be a little into the economics here. These forest pests are the things that are of more concern perhaps than the bugs biting us. They're responding to the same issues. These become economic issues. And here's the agricultural, and then I'm going to one more and get to solutions. But agricultural issues we model, and you've heard the wheat belt will do fine. It'll just move a little north, and that's fine in North America. There's a few things left out of that model. First of all, there's the extremes, the droughts and the floods. There's the early heat waves in early May when the flowering the plants. And so the timing of events. And then there's the other issues, the pests, the pathogens, and the weeds. Here's one that came into the U.S. on the tails of Hurricane Ivan. You may have forgotten that we had 4 hurricanes that hit Florida in 2004. This was before Katrina, Wilma, and Rita. And the range can be affected by warming. So warming affects the range. Weather affects the timing, the intensity, location of outbreaks, and even the kind of outbreaks, because floods give you fungi. Fungal growth, like this Asian soybean rust, is the biggest blight of pests, of crops. And then droughts can give you other problems. Aphids, whiteflies, and locust. Mere mention of locust shakes anyone. The sum of this issue is that 42% of growing and stored grains are damaged and destroyed by crops, pests, pathogens, and weeds every year. 42%, that's equivalent to about $300 billion on international markets, be it stored grains and fleas, rodents, so on, or growing. So this is a very important issue in terms of thinking about the nonlinear potential, the potential for nonlinear changes in crop yields. Here's one that I just take a little tangent to talk about Africa and carbon dioxide and warming and drought. Yucca, tapioca is one of the staples that fills the belly of folks. Here's in Mozambique in 1981, a drought. I worked in the late 70s in Mozambique as a physician. Here's what happened, and this is the worst picture I'll show you. From eating early crops, early tapioca, yucca. Cyanide is in the plant. Why is it there? Well, that keeps the bugs away. It's part of the defense of the plant. If you harvest this early, don't process it, people are malnourished, you get neurological poisoning. Now what we've learned in experiments in Australia is that increased CO2 also increases the cyanide in the leaves. The leaves is not what we eat, what I was mentioning, but we do eat the leaves with coconut and peanuts. It's a great mixture called matapa that you add to rice and a little bit of meat that if you have it, or fish. So it is eaten. So this is another issue that we weren't aware of. CO2 has effects on plants. Here's the yields of CO2, and this needs to be reproduced in the field. So let me sum up the problems here. Thinking about our backyard and the backyard of the people that you relate to. Let's start with just CO2. Put aside the global warming, climate change, the whole thing for a moment. Just more carbon dioxide affects plants in ways that we hadn't known. We took ragweed and put it under double CO2. The stalks went up 10%, pollen went up 61%. US FDA has done this, was doing it simultaneously, and they find the same results. It turns out that weeds like carbon dioxide, put it into their male territorial seeking selves, the pollen, that's how they spread themselves. And so that may be why this happens evolutionarily, teleologically. The pollen, however, become more toxic and more allergenic, and they also are food for mosquitoes, so that's another side tale here. But they are more allergenic. Agricultural weeds. Remember I mentioned pests, pathogens, and weeds. CO2, agricultural weeds. Think herbicides, insecticides, pesticides. Not what we want to go to with our organic agriculture. So that's another health dimension. Tree pollen in the spring. Spring is tree season, tree allergy season. Grass for the summer, weeds, ragweed principally for the fall. And we've got an extension of the season. It's about 20 days now, recently published in Science, between spring and fall. And then we get some spores, and here's some nasty synergies. Ozone, also from burning fossil fuels. NOxes, goes up in heat waves. And then here's the nastiest picture here, which is the diesel particles that are about these black carbon that are PM 2.5 or 10, attached to the pollen, which are PM 10s. And they're delivered deep in our lungs. They irritate the mast cells that cause the allergic phenomenon because there's nitrates in the diesel. I'm going to add this up for a moment just to be clear. Burning fossil fuels and CO2, burning fossil fuels and NOxes and smog, burning fossil fuels and particles, burning fossil fuels in the aggregate of climate change affecting the seasons. Burning fossil fuels is the issue. How we burn less of everything is going to be part of the solution. Mold mentioned, poison ivy is getting stronger, published in the PNAS, Proceeding National Academy of Sciences. Also the chemical within it, urushiol, so similar reaction. Lime, I'm not going to persist on, but here we go with the last one. I put a star just to say something good about disease, because I haven't been very kind. You'll notice the crows that were around about 10 years ago that were mobbing the trees and they were accumulating in the trees and mobbing the hawks and so on, have gone. In fact, they've been documented. They're down about 45%. This is 3 years ago, published in Science, because of West Nile. That may have opened up the ecological niches in the city for all the lovely little, nicely sounding, attractive birds we're seeing, like cardinals. So disease can play a good role at some point. And if anyone finds something for Canada Goose, let me know. That's not for public audience. All right, so CO2. So what do we do about this? Well, there's one other area before we talk about solutions that we often leave out, is our energy infrastructure. And it too is vulnerable to climate change. So as we think about adaptation to climate change, this community over here, and the mitigation community that's over here, and the red community that's in the middle, reduced emissions from deforestation and degradation, those three communities seem to be going hopefully somewhere parallel, but they're not together. Here we are with storms and interruptions, still from Katrina, Wilma, and in fact Ivan the year before. Pipelines, oil rigs, and refineries, it's down 25%. And traders on Wall Street who are trading in energy futures are looking at storm tracks. Blackouts, the 2003 heat wave in Europe also affected the U.S. And let me say one thing about heat waves, because that's what we often associate with health and climate change, and we're looking at a summer here. There are two things about heat waves that climate change affects. It's not just their intensity and their breadth and their frequency, but it's the warming at night, the T minimum story. Nighttime winter temperatures have gone up twice as fast as overall warming since 1970. It's the lack of relief at night, that's when the cows go down in the west, when there's no relief at night. It's what affects us. It's what happened in Chicago. And then there's the humidity story that I mentioned with the hydrological cycle and warming of the atmosphere. So climate change means that the characteristics of heat waves are different. It means that as we prepare, it's not only air-conditioned malls and lovely rooms like this, it's air-conditioned hotels that we need for surge capacity. We've got to think of this in terms of the public health responses. 24 out of 104 of our nuclear power plants are in places where aquifers are already overdrawn and underfed. Heat waves clearly will affect their water temperature. That's what happened in France. Many of them had to shut down, as well as droughts that you just heard about can affect our vulnerability in terms of those that we have already. Pipelines in Alaska are buckling, some of them, because of the melting of the permafrost. Lightning has gone up with warming, and this is from the Hartford Boiler Insurance Company, just published, though, however, in scientific literature, this association. And here's this more sobering issue of hydropower, water coming from the mountains for agriculture, for health, but also for power. In Peru, they're making plans for coal-fired plants to replace their lost hydropower. This is clearly a huge, huge issue in Asia with the Tibetan Plateau. So what do we do about all of this? And this is where you're grappling. I would say where we are right now, if we think about the science and what it's telling us to do, I think this community and Washington, we're all moved through that. As to what are the solutions, we haven't quite gotten our hands around that. We're in the middle of what's the policy instruments to drive whatever we do. So this is not focusing on that, but I will end with some comments about that. But here's the schema that was developed at Princeton by Steve Pakala and Rob Sokolow of all these ways to bend the curve, to stabilize the concentrations. First, stabilize the emissions, then the concentrations of CO2 and CO2 equivalent. So here they are. Now I'm going to look at these not just from a technical perspective and economic, but a health and environmental lens. Now that may sound still a little fluffy. Okay, what are we worried about the health issues? But the health and environmental issues turn out to be what Swiss Re is looking at, what AIG, what all the insurers are looking at, Zurich Insurance, what bankers who invest in Wells Fargo and Bank of America and JP Morgan Chase and Credit Suisse, Morgan Stanley, those are the 5 originators of the carbon principles. They remember the long tails, precautionary long tails of asbestos, tobacco, lead, industrial toxins. So if we don't think ahead, we're going to have problems we didn't anticipate. On the other hand, there's a whole lot of things we can do that are good for public health, good for the economy, good for the climate. I'm going to list the 15 of them here. All of the wonderful things that we know are good for us in the first place. Efficiency, conservation, they save money. Renewables, PV, solar, there are issues within those like siting of wind and so on, but in general, we know these are the directions we have to go in. Natural sinks, conservation tillage, forest nurturing, another wedge of avoided carbon emissions. Each wedge, 1 billion tons avoided, 1 gigaton. And we may need bigger wedges, but the idea is this is a portfolio. Then there's the fossil fuel-based and nuclear. That's the gamut. There are new ones coming up like waste disposal and capture of methane, and that's the cleanest burning fossil fuel. So there are others that are being developed now, but this is the heart of it. So what are no regrets? What can we put? Everything's on the table. We haven't taken nuclear. We haven't done anything. We've separated between what can we do now that's really good, that we know has lots of promise, lots of opportunities, and what do we need to study? So here we are. Well, we're over 7 with things that we know are good for us. The 2 on the left, forests and agriculture, those are huge ones. How do we incentivize, get our policy instruments, financial mechanisms lined up for those? That's not so easy to solve, and there's our red trying to work that out. Agriculture is a big one, and 5/6 of agricultural emissions come from clearing land to grow seed or graze. That's the main issue with agriculture. And then, as I said, there are issues to look at, geothermal and so on. Is it safe, so on. But in general, we have a whole lot of things we could be doing. On the other hand, biofuels, some issues with biofuels. Fossil fuel-based, I'm suggesting we have to study hard. And then nuclear fission, just giving 3 S's here. The Healthy Solutions Report you may have picked up goes through this. But here's a quick summary. We think about nuclear and carbon capture and storage is about all we're hearing now as if these don't work out. So let's just think about those for a moment. Nuclear fission, storage, safety, and security. Safety's probably the least of it. We know pebble technologies, we can get there. Security is a huge issue, particularly if we double what we have now and get a wedge. There's going to be more of this on the roads, and we think we can put in yucca or something like it, 70,000 or 140,000. None of that takes into account decommissioned plants. So that's a big issue, and it's perhaps being solved in Sweden only. France has not solved this permanent storage either. And then there's the other two stars I put up there, 10 to 12 billion apiece, 10 to 12 years to build them. Takes 2 years to build wind farms and solar and so on. This is not a rapid response. This is not something without a lot of fossil fuels put into it to build the plants, to get the uranium. It's not a renewable resource. So there are lots of problems that we have to be thinking ahead before we give our subsidies and our government insurance plan to expand a wedge. Here's what we're trying to do with figuring out with liquid fuels. So here are the technologies, again, warranting this life cycle analysis. So we've gone through nuclear, going to take a look at biofuels in here. Liquid fuels, to replace them, we're looking at all of these shale oil, tar sands, lots of issues with those in terms of water and energy use. Here's the life cycle of oil: extraction, transport, refineries, transport again of refined, and then combustion, and then we burn it, and so on. All of these stages is what's leading to what's happening today in Peru, in Ecuador, and the uprising of people because of the headwaters of the Amazon with oil exploration. We have not come to grips with the ecological dimensions of our addiction to oil. And I would remind us, our last president said we are addicted to oil, and that's the first of a 12-step program. So here we are, making that program. But the biofuels issue, there's a lot to be said about land use and food security and so on. But the one I want to highlight here is the health issue. Burning mixtures of ethanol and gasoline gives you formaldehyde and aldehyde, acetaldehyde. These are volatile organic compounds. This is the one you will remember from your labs. They combine with the NOxes to give you ozone. Ozone, there's 3 types of ozone. There's the good, the bad, and the ugly. There's the good stuff. This is Kevin Trenberth from NCAR. Good stuff is in the stratosphere. The bad stuff is in greenhouse gas. The ugly stuff is photochemical smog. In the cities, it's contributing to the heat island effect of trapping heat in the cities. It's corrosive to the lungs. It's worsening our adaptation to climate change. Biofuels are going to worsen our adaptation to climate change. We have to think about that dimension of the life cycle. They've known about this in Sao Paulo, Brazil for many years. We're now studying it again, but this is not an unknown among respiratory physicians and air pollution specialists. Nuclear, biofuels, questions. The third one is coal. So here I'm touching on lots of toes in this nation because we are trying to bring the coal industry into this century. But here's the life cycle. Underground mining, lots of problems for health, silicosis, so on, injuries. Then we come to mountaintop removal, deforestation, reporting of cancer clusters with the waters contaminated. This is a big issue. Retention ponds we just became aware of on December 22nd, 3 days before Christmas. That's when the TVA, Tennessee Valley Authority, went. We didn't know they were there. Well, they happen to be all around coal-fired plants. They're all around the refineries, meaning pulverized coal. They're all around these mountaintop removals. Sludge and slurry. The ponds are retained with hardened sludge and slurry. This is not secure in any way. 70% of our rail traffic is taken up with coal. Imagine what we could do with that, with getting public transport. Then we burn the stuff. And NOxes, I want to call attention. First, mercury, 48 tons of mercury, and that's a huge issue for all of us. But this is one that gets little attention. Nitrogen coming into our coast, in the East Coast, half of it's from coal-fired plants. The other half is non-point sources from agriculture and point sources, sanitation, sewage. Half of it. Half of the nitrogen in this nation. It's probably a lot more in the China South Sea and the Bay of Bengal from India. They're losing their fisheries. They're creating dead zones from burning all the coal, just as we are. This is an issue now, dead zones throughout the world. Coal is a contributor to that and to our fisheries. And then finally, we're going to bury this. So just for a moment, think about clean coal, and think about all of this before we get to this issue of CCS. Can we do that successfully? That's the next issue. But does that answer this question? I'll leave that as vague as I did. Here's what's up in these mountains, just to give you a glimpse of it. I just went to Kentucky. This is the size of these. This is what's happening up in these mountains. This is what you see. They've just blasted the top off these. First, the trees and all the stuff is pushed into the side. Here's the lovely towheads in the bottom. And here's what happened after a 2-inch rain 5 days before I got there. All these trees, all these boulders down in people's lawns, in their streams, on their houses, on themselves sometimes. This is creating zones of vulnerable populations. Mountain top removal is a misnomer. It's mountain range removal. These are ranges, and this is the kind of extent of this, and this is creating this vulnerability. It's changing the local climate, just as what we're doing in the Amazon changes the hydrological regime there. This is serious stuff that makes you wonder what you hear from the industry. I'll leave that as it is. So how are we going to do this CCS, just to take that on its own? Putting the carbon underground, here's where we first proposed to do it. Coal, oil, these hydrocarbon reservoirs. That's where a lot of the pilots are going to be. We might get methane. That could be a good thing. That's the cleanest burning fossil fuel. But here's the big reservoir, saline aquifers. What's happening to saline with carbon dioxide? What's happening to the oceans? Carbon dioxide in the oceans is acidifying the oceans. It's 30% down in its pH than it was pre-industrially. It's not trivial. It's still basic. It's 0.1 pH scale, but it's 30%, and I'm quoting Tom Lovejoy in that analysis. It'll do the same thing with saline aquifers underground. That can leach arsenic and lead into the saline, into the groundwater. That's a health issue. But the bigger issue is what it does to microbial communities, other gases, and limestone. Limestone is chalk, calcium carbonate, and with more acidification, we're going to actually disintegrate that CO2. So can we find enough plates to put this under? This is a whole issue in terms of, is this secure and is this insurable? Saline aquifers have some connection to the outside, and then this is the calculations of Ed Rubin at Carnegie Mellon, that with 1 gigaton, we'd need 5,000 square miles. This is a big issue. How we study this locally is one thing. How we extrapolate and figure out, can we do the abundance in saline, is quite another question that I'm concerned we're not going to be able to answer with our local experiments. And just a few words on climate meddling, I'll put this. Geoengineering. Sulfates in space, we have to worry about more acidification. We have to worry about crop yields. Mist is another one proposed, and I am going to come to what I think we can do. We'll end with that. Plankton at sea, we've really measured it 100 meters down. That's the photic zone that we've known really doesn't quite work. CO2 removal and scrubbing, that might actually be something we have to get to, and we'll have to bury some of that or sequester it. And solar panels in space, I just want to mention, because this isn't really geoengineering, but this is, with microwave, this is a source of energy. And this is the one that I think we should give the maximum attention to. That may be something that boosts the solar energy. So what can we do? Well, with traffic, transport, with cars, trucks, and we need to change from the internal combustion engine to electric vehicles, plug-in hybrid electric vehicles, lawnmowers, caterpillars, all of this stuff. But that has to plug into somewhere. So here's our cleanly powered smart grid that many of you are getting involved in. And to complement that, healthy cities and connected with light rail. This is where we could put our stimulus packages into the healthy cities, into the grid, and helping Detroit become something different. What is a cleanly powered smart grid? Multiple means of distributed generation at each site, so redundant species, resilience, complementary systems of triangulation, capturing heat, two-thirds of the energy is lost from heat at any plant, capturing it in steam and so on. Smart technologies to manage this, smart within cities. We can all be fractals of this so that every center, every institution, every house, every university can be fractals of a grid that gets smarter and then plugs into the grid. So this is a project that we can all be part of. And here are the cleanly powered ways to do this with hydro and natural gas as the buyout. And I want to mention Ken Zweibel's paper in Scientific American, January 2008, a grand solar plan, phased-in plan. It's a model of how we could get to where we need to go with wind, 85% of the grid by mid-century. A word on green chemistry, because we have to get off petrochemicals for here's our bioplastics, you shred it, and here's BioWilly. But we need to get off of food sources, so algae and tobacco is another one for all of these things. We don't have time to belabor all that. I want to mention the healthy cities for a moment and end with the positive things here. Here's what's trapped under, but this is part of the solutions. Green roofs, green buildings, tree-lined streets, biking lanes, walking paths, open space, smart growth, public transport. They're all about creating jobs, creating new industries, decreasing these heat-trapping CO2 in the city, ozone, black carbon now we know, cleaning up our cities. They're healthy, they're job creating, and they advance these technologies for climate stabilization. Here's one that's a really easy one to do, and dark roofs have this temperature off them. In Chicago, this was measured, so white roofs is something that we could do. And in developing nations, we need energy for development. Development is needed for adaptation. When the wind doesn't blow and the sun doesn't shine, we have a rope around it and ride it with our motorcycle. All these MDGs that we hold so dear, the Millennium Development Goals, except maybe one, gender equality. Maybe we can work that out ourselves, but the rest, we need energy for water and cooking and so on. We've got confluent crises. We're a lot of failing Fs here, and we've got to deal with all of them at the same time. This is our challenge for today, our challenge for this these days, this can create a confluence of agendas. It's this clean development, clean energy as the first necessary step towards sustainable development. Here's your Washington consensus, and this is the penultimate slide. This is what we've gone on for the last, some people think 500 years. We need more regulation. We're finding that out in the financial markets. We need public-private partnership writ large. We need more constraints on the way we function, and not on goods, but control over investments and the flow of international capital. We learned that from Bretton Woods, that we needed rules, fixed exchange rates, and constraints on the transfer of capital. It couldn't just go into Tokyo, out to Singapore, and then to Bangkok in 5 seconds on the computer. You need to make investments that last. And that was one of John Maynard Keynes' insights. To solve the whole thing, we don't have to really figure out the whole thing. We just have to change the rules. That was one of the key rules that was relaxed by Nixon in 1971. We need to deal with a whole lot of other issues that we hadn't had to deal with back in '44, like debt, terms of trade, tariffs and subsidies, swords with no shields denied. So finally, how do we do all these wonderful things I'm suggesting we have to think about? We need carrots, we need sticks. We need an institutional framework. We need to realign the rewards, the rules, the regulations. There's only some things the public sector can do, like large procurement practices and fleets and so on, and infrastructure. We need a comprehensive plan that's phased in. We have some strong lobbies, not coincidentally with those three things I suggested we put on this side of the table to study. If we get them to the side and think about rationally with a life cycle analysis what we can do now, this can be the engine for the 21st century. We've got to lead with those carrots. We're going to need institutional framework that's a little different than what we have now, and we need regulations, all of those. If we do this right, it can be good for public health, good for security, good for the economy, and we certainly hope it'll stabilize the climate. Here's our websites, and thank you very much.
Terrific. Well, thank you very much, Professor. You really, it was a tour de force in terms of covering a whole range of issues. To call it just health and climate does it a disservice in terms of the topics that you touched on. Let's go immediately to questions. I certainly have a number, but I'm sure the audience does as well. Because we're recording the video, I ask that you wait for one of my colleagues to come to you with a microphone so that everyone can hear it, but we also capture it for the video. So Rachel, I think we'll start right down here if your mic is working.
Hi.
And if you could everybody let us know who you are.
Yes.
Hello,
Please.
can you hear me?
Yep.
Okay. I'm Bianca DeLille from Science Communication Network, and my biggest concern is that we won't have enough water to change to renewable energy. Doesn't, except for solar, most everything going to require some water, and we're running out?
Well, thank you, and thank you for all for your patience and staying power. Water, I think, yes, I agree. Water is one of the major issues, and there are conflicts and so on. It can also be a driver, because desalinization of our rising seas and irrigation of lands may be something we're going to have to go towards big time, and that can be done with solar power. So I'm hopeful that that problem becomes a part of a driver of the solutions. You are right about solar, actually. It doesn't necessarily need water. Even the concentrated solar power arrays, which now can be made with plastic and polymers instead of glass, so bigger, can be cleaned with dust balls. You don't necessarily need even water for those. So solar may be free of that. constraint.
Jason Bremner in the back.
Thanks for your talk. I noticed in the wedges, those are mostly technology wedges, and I'm wondering what you think of some discussions of family planning, access to voluntary family planning, and meeting that need of millions of women around the world as a potential wedge. I know it's been discussed.
Yeah, we should say as context, we've had Brian O'Neill from NCAR here at the center discussing this issue.
Well, good. That's an excellent addition, and that's an interesting way to frame it in terms of the wedges. Clearly, there's a lot of population issues behind all of this that need to be addressed, and some of them are with interventions like family planning, education for young women, so on. The other part of the discussion of population, I think, has to be development. And development, when nations start developing, is when they really can control their populations in a healthy way. So it's not whether to develop, it's how to develop and how to power that development as a way of dealing with the economic dimensions that underlie some of the population issue. I want to remind us the population density of Bangladesh is exactly the same as the Netherlands. So now that's not a completely fair comparison because of resources and trade and so on, but there are lots of things that we have to think about population, but the economics has to be a big part of that discussion.
Could I ask a follow-up on that? Because you said early in your talk the challenge of bridging the communities of mitigation, RED, and adaptation, and how that wasn't happening, and I couldn't agree more. And I think certainly in the context of the year of Kyoto and a very heavy focus on mitigation, and just kind of knowing who's in the chair in those negotiations, it's not the adaptation of the development community, which you're pointing out, I think quite rightly, is critical to some of this. How do you see, or what are the pathways you see that are likely to help build those bridges and really pursue adaptation? I mean, assuming we can find some money, and I thought it was particularly interesting on Amanda's slide about where the money was implied. It was a very thin strip for international, and so the kind of question of whether the rest of the world is going to go along with any sort of global agreement if this is as tiny little slice as what we're willing to put on the table on the adaptation side. But anyway, your thoughts on the kind of constructive ways to bring those communities together?
Well, that's a great question, and perhaps that's something the Woodrow Wilson Institute could play a part in convening those kinds of discussions, because I do see that there are material issues that are common to both adaptation and mitigation. We need forests. We need healthy, intact forests for adaptation to storms, to preserve the soils, to preserve the carbon we have there, to preserve the animals, to preserve the water, so on. So it's necessary for adaptation and mitigation. Mitigation being 20% of the problem. So we have a 5 gigaton carbon problem. There's about 10 released every year, 8 from fossil fuels, 2 from forests, 5 goes into the ocean, and the land, we're left with 5. So clearly forests are a key part of the climate issue. The second thing that's omitted, and I don't quite understand, is why the adaptation community is not talking about the need for robust, resilient energy systems to prepare for the coming climate. It's certainly critical with heat waves. We're going to need distributed energy to keep our AC going. And while we're doing that, we might as well get some ground source heat pumps that's AC and warming. So that pushes us towards that. We need energy for development, as talked about, and that's key for nations' ability to adapt. We're going to need distributed and robust systems to deal with interruptions to power, to the kind of ice storm that we had, from Kentucky all the way up to New Hampshire this winter, and more rains falling at high latitudes, and then we get cold snaps and we get ice storms. So we're worried in this winter about orthopedic weather and traveling and so on. These are issues of weather instability is a key thing in terms of winter weather anomalies. So these are the issues that, and storms, and then so on, ice melt, all of these, we're vulnerable. So clean, robust, resilient energy systems are necessary for adaptation and to prepare resilient communities. I think we're missing that dimension of the vulnerability of the energy infrastructure. So those are two areas that I would hope that could help bring these communities together and think about one program that meets these. Think about a global fund for adaptation and mitigation in red. Think about these as how they are what are the complementary issues.
Terrific. So, okay, thank you.
Thank you.
Yes, the gentleman over here.
Hi, Paul. It was a great presentation. Thank you very much.
Good to see you.
I'm Jim Listorti. I'm an environmental health consultant at the World Bank. Observation or question for you. I mean, what we need to have happen is behavioral change. And I'm wondering if there's enough people worrying about getting the message out to the average consumer, particularly American, the person who shops at Walmart, about how, because for them, you know, it's climate change may be a problem of tomorrow. Americans are pretty good at responding when there's a crisis. Gasoline prices went up, people conserved. There's a water crisis, people conserve. But when the crisis is gone, back to behavior, and wastefulness. And I'm not sure that there's enough people worrying about the message, getting it out to the right audience. There's a lot of people worrying about what goes into the message. There's a lot of people worrying about the science, but is there enough people worrying about how you get the message out?
Good. Well, thank you. And people have talked about a behavioral wedge, too, and there's certainly so much we can all be doing. And I couldn't agree with you more. And I would say we also need to get the incentive structures lined up so that people are encouraged to do the right thing. And when you leave your house, there is a system that shuts it down except for the refrigerator. And when you go out of the factory, it cools it down. You know, you get the idea. We need those systems in place so that it's not just the individual that we're relying on. We've learned from public health that campaigns for vaccinations have a problem. We've done campaigns and get your tetanus shots and give the food and well, they forgot to buy enough tetanus vaccine. You need the thing that you want the people. It's sort of very simplistic and obvious, but you get the idea. We need the means to do those things that we want people to do, and it's got to become a general norm. At the same time, yes, we need a lot of education going on in all levels of schools right now about how to adjust to a world with very different patterns of consumption and different kinds of growth.
Yeah, it's interesting. I think Andy Revkin's .Earth column yesterday or today is devoted exactly to this communications question and has a number of interesting citations. And I'm sure this report that's coming out today that's really trying to say, okay, in the Pacific Northwest, here's what is happening now and here's what's coming, to try to, and then kind of for all regions in different sectors, try to move beyond some, as you say, remote things like, well, global average mean temperature change or a sea level rise that has people have a hard time, okay, what does that mean to me and my community? Right. That this report, I think the hope is in part that they will make that much more real and capture the imaginations and provide some of that added incentive for individual behavioral change. Yes, ma'am, right in the middle.
Thank Thank you very much for that presentation. My name is Gabriela Stockmeyer, and I'm with the Environmental Law Institute. And I'm wondering if you can touch a little bit on the health and environmental impacts of renewable resources. You hear so much. I mean, you brought up unintended consequences, but what about concentrated solar power? What about the health impacts of the materials needed? And it doesn't come up, and I'm wondering if you can touch on that a little.
Good. No, that's a very important question, and if we're going to subject all the things to life cycle analysis, we have to do that with the things that I'm saying are good to do. I just had the treat of visiting a 3M headquarters, which 3M is on our corporate council, along with Swiss Re. And they're developing some films for these concentrated solar power that is very different than the glass. I won't give it all away. It's probably trade secrets that I'm not supposed to be giving away. But there are materials being developed with polymers that are much easier, cheaper, greater surface area, and going to be much better. Are they safe? We talked about using plant feedstocks for these polymers. And then you run into, well, plant feedstocks is biodegradable, so is that really durable? So how do you deal with all of these? These are things that the industry is beginning to deal with, of how to develop things that are non-toxic. And there's a whole field of green chemistry that's paralleling this whole process of getting off petrochemicals and persistent organic pollutants and so on, that I think has to go along with this process of solar cells as well as concentrated solar. They're making other films at 3M for the wind turbines that make them go faster and cut the work. Can you make those out of plant feedstocks? These are the questions that we do have to ask. So I don't. It's something we should be doing, but it's at parallel. I think this R&D and so on has to go towards how to get us into another set of materials that are non-toxic.
Okay, John is right there.
This is sort of loosely related to the behavioral change comment that the gentleman over there brought up. On your Bretton Woods 2 slide, you mentioned, and I'm not entirely clear on your exact phrasing, but you mentioned something along the lines of setting up a framework that would encourage more long-term investment as opposed to short-term investment.
Right.
And so I was just wondering if you would maybe elaborate on that, or perhaps drop some names of some people who are directly working on that problem.
And if you could let us know your name, sir.
Oh, my name's Christopher Kraus from the National Environmental Education Foundation.
Terrific, thanks.
Thank you, Chris. That's now you're where I want to, my heart is, how to think about how to reset the rules. First of all, Bretton Woods. This was 1944. People realized this is not working. 2 world wars, the Great Depression, it's broken down. And with Keynes as the visible hand, had all of the nations agree to 3 rules. It was free trade in goods, fixed exchange rates, and constraints on the international exchange in capital. And a couple of names to throw out is Adam Smith and David Ricardo, who both talked about the issue, if there is transfer of funds freely, it destabilizes everything I just said about competitive advantage and comparative advantage and competition among nations. If you transfer this money in and out of countries rather than being an investment. And this is what happened, well, in 1971 with the pressures of Vietnam War, the inflation, fixed exchange rates were abandoned, they floated, oil went from $3 to $30. That sounds good today, but it was tenfold. Gold went from 38, which it was for $1, to over 600. and it's about 1,000 today. So a lot of the things came unhinged in 1971. We had the rules. We had institutions set up, the International Monetary Fund, the World Bank, the GATT, which was 1947, the Global Agreement on Trade, help me, Jim. Tariffs, thank you. And I will remind us that other wonderful institution we all have that followed the League of Nations from Woodrow Wilson was the United Nations. They all got set. That institutional framework was critical, clearly, for the post-war era. And then the third part is the funds. And we had the Marshall Fund for Europe. We had the GI Bill in this nation, which funded schools, housing, jobs. So these were the stimulus. This was the deficit funding that we're doing now that catapulted. So we had rules, we had incentives, rewards, and we had institutions. And 71, that all came unhinged. And as we went into the petrodollars, the specudollars, and so on of the 90s, and the debt crisis, I'll be glad to communicate with you more on the details of all this. But here we are, and 98 was the fall of the bot. That was the fall of that. That was the last bubble that burst. And Malaysia was one of the only countries that survived that because they had constraints on capital flow. And that was criticized by the World Bank and then recognized by the World Bank 5 years later. Let me end this with some numbers. The trade on currencies in 1972 was $18 billion a day. That's rubles versus dollars versus yen, pesos, gaming. Today it's about, well, the end of the 90s, it was $2 trillion a day. Yeah, and it's closer to 3 now, so that's a good question. I don't know how that's adjusted, but in today's dollars, it's somewhere up there. Per day, it was 1.9 by 98. James Tobin, Nobel Prize winning economist, proposed the Tobin tax, the tax on that currency. And the reason was to slow down this wanton transfer of movement of capital investments among nations. And incidentally, later, people calculated, goodness, maybe we could generate some money out of that and have a global fund for the global commons and sustainability project we have to start into. So he proposed like 1/4 cent on a dollar. Today's dollars would get you something like $300 or $400 billion a year, which is the kind of money that Stern talked about in his review 3 years ago now. $350 billion a year for some years. That's 1% of global GDP, as opposed to we're going to lose 5 to 20%, meaning $1.75 to $7 trillion a year from the impacts of climate change, from the nonlinears. So we're in the ballpark of where we could get for a fund for adaptation, mitigation, and RED. It would slow down the transport, and that would probably be a good thing as well.
Okay, well, I think we've come about to the end of our time. It's been a very rich set of presentations and some very good questions. We appreciate that from the audience. We will have summary PowerPoints and video on our website. We hope you will come visit that, as well as, of course, Dr. Epstein's website that you've had up on the screen. Critical topic, one that we really appreciate your leadership on it, because you really have been a leader on this, and it's a critical set of questions that fortunately are actually above the fold now in terms of the attention that they're getting. Let's hope that they are not just talking but actually acting in some of the ways that we've heard today. So please join me in thanking Dr. Epstein for her presentation.